Let me tell you something about physics that most people never learn, even though it's probably the most beautiful idea in all of science. I've been thinking about this for years, and every time I come back to it, I get excited all over again. You see, there's a pattern hiding underneath everything. Gravity, electromagnetism, quantum mechanics, the motion of planets, the way a ball bounces, all of it. And once you see this pattern, you can never unsee it. I remember when I first really understood this. I was maybe 25, working on some problem that I don't even remember now, and it hit me like a ton of bricks. All these separate things I'd learned, all these different laws and equations and rules, they weren't separate at all. They were all connected by something deeper, something hidden in plain sight. Now, the thing is, most physics classes teach you the laws one at a time. Here's Newton's laws of motion. Here's conservation of energy. Here's conservation of momentum. And you memorize them, you use them, you pass your exams. But nobody tells you why these laws exist. Nobody tells you there's a reason behind the reason. And that's a shame, because the reason is gorgeous. So let me explain what I figured out. And I want to be clear, I didn't discover this. A mathematician named Emmy Noether figured this out back in 1915, and she was brilliant. Absolutely brilliant. But the physics community didn't pay enough attention to her because, well, she was a woman and it was 1915, and people were idiots about that kind of thing. But her theorem, Noether's theorem, it's one of the most profound things ever written down. And I'm going to tell you what it means in plain English. Here's the basic idea. Every symmetry in nature corresponds to a conservation law. Let me say that again because it's important. Every symmetry gives you a conservation law. If the laws of physics don't change when you do something, when you shift something or rotate something or wait a while, then there's something that has to stay the same. Something is conserved. Now, what do I mean by symmetry? Most people think of symmetry as, a butterfly's wings or a pretty pattern, but in physics, symmetry means something more specific. It means the laws don't change when you transform the situation in some way. And that's where it gets interesting. Let's start with the simplest example, spatial symmetry. What do I mean by that? Well, suppose I set up an experiment here in my laboratory in Pasadena. I measure how things work, the forces, the motions, all of it. Now suppose my friend sets up the exact same experiment in New York, same equipment, same conditions, everything identical. The question is, will the laws of physics be the same in New York as they are in Pasadena? You might say, well, of course they will. That's obvious. But think about it for a second. Why should they be? Why should the universe care whether you're in Pasadena or New York or on the moon? There's no law that says the universe has to behave the same everywhere, but it does. As far as we can tell, the laws of physics are the same at every point in space. That's spatial symmetry. The laws don't change when you shift your position. And here's the kicker. Because the laws are the same everywhere in space, momentum is conserved. That's Noether's theorem at work. The symmetry of space, the fact that physics works the same whether you're here or there, that's directly connected to the conservation of momentum. It's not a coincidence. It's not two separate facts. They're the same fact, looked at from different angles. Let me explain why this makes sense. Imagine you're floating in empty space, far from any stars or planets. Nothing around you for billions of miles. Now, which direction is special? Is there something about left that makes it different from right? Is up different from down? No. In empty space, all directions are equivalent. There's no preferred direction. That's rotational symmetry. And it's connected to the conservation of angular momentum. But let's stay with the simpler case first. If the laws of physics are the same everywhere, then nothing can tell you where you are in absolute terms. There's no cosmic address, no grid painted on the universe. And because there's no preferred position, when things interact, the total momentum can't change. If it could change, if momentum could appear from nowhere, that would mean something special about that location. It would mean the universe was different there. But it isn't. So momentum is conserved. Now, this might seem abstract, so let me give you a concrete example. Take two billiard balls. They roll toward each other on a table, they collide, they bounce off. Before the collision, ball 1 has some momentum, ball 2 has some momentum. After the collision, they each have different momenta. But if you add up the total before and after, it's the same the total momentum is conserved. Why? Because the collision could have happened anywhere on the table. It could have happened on a table in China. The physics doesn't care about the location. The laws are symmetric under translation in space. And that's symmetry. That's what guarantees momentum conservation. It's beautiful, isn't it? Now, let's move to something even more interesting, time symmetry. What do I mean by that? Well, suppose I do an experiment today. I measure everything carefully. Then I wait a year and I do the exact same experiment again. Same conditions, same setup. Will the laws of physics be the same? Will my results match? Again, you might say, obviously yes, but why should they? Why should the universe work the same way tomorrow as it does today? There's no guarantee written into the fabric of reality. But as far as we can tell, the laws don't change with time. An experiment done in ancient Egypt would give the same results as one done today. The laws of physics are symmetric under translation in time. And what does this symmetry give us? Energy conservation. The fact that energy is conserved, that energy can't be created or destroyed, that's directly connected to the fact that the laws of physics don't change over time. Again, these aren't two separate facts. They're the same deep truth. Think about it this way. If you could build a perpetual motion machine, a machine that creates energy from nothing, that would mean the laws were different at different times. Today you can't get energy from nothing. But tomorrow, in your magic machine, suddenly you can. The laws would have changed. But the laws don't change. They're the same yesterday, today, and tomorrow. So energy is conserved. I spent a lot of time thinking about this when I was younger, and I kept finding more examples. Rotational symmetry, the fact that the laws are the same regardless of which direction you're facing, that gives you conservation of angular momentum. The symmetry of electric charge gives you conservation of charge. Every time you find a symmetry, you find a conservation law. Every single time. And here's what really gets me excited. This works the other way too. If you discover a conservation law, you can ask, what's the symmetry? What feature of the universe is the same when you transform things in a certain way? The conservation law is like a fingerprint. It tells you something deep about the structure of nature. When I was working on quantum electrodynamics, this idea kept coming up. The conservation of electric charge, which we observe everywhere, it's connected to something called gauge symmetry. Now, gauge symmetry is a bit more abstract than spatial or time symmetry, but it's the same basic idea. There's a transformation you can do, a way of shifting things, and the physics stays the same. That symmetry guarantees charge conservation. What's wonderful about this is that it connects things that seem completely unrelated. Look, when you first learn physics, you learn about forces and motions and energies and momenta. They all seem like separate concepts, separate tools in a toolbox. But Noether's theorem shows you they're all manifestations of the same underlying structure. The universe has symmetries, and those symmetries create the rules we observe. Let me give you another example to make this concrete. Think about a ball thrown in the air. It goes up, slows down, stops for an instant at the top, then falls back down. At every moment, its kinetic energy, the energy of motion, is changing. At the bottom, it's moving fast. At the top, it's not moving at all. So kinetic energy is not conserved. But wait, I said, energy is conserved. What's going on? The answer is that kinetic energy isn't the whole story. When the ball is at the top, it has potential energy, energy due to its position in the gravitational field. And if you add up kinetic energy and potential energy, the total is constant throughout the flight. Energy is conserved, but it transforms from one form to another. The ball trades kinetic energy for potential energy on the way up, and potential energy for kinetic energy on the way down. The total never changes. Why? Because the gravitational field isn't changing with time. If gravity were getting stronger every minute, then energy wouldn't be conserved. You could set up situations where energy appeared from nowhere, but gravity is constant. The laws are the same now as they were a moment ago. Time symmetry, energy conservation. Now, I want to be honest about something. When I first learned about Noether's theorem, I didn't fully appreciate it. I thought, okay, that's a nice mathematical result, but so what? I was young and arrogant, and I thought the important thing was calculating things, predicting experimental results, getting numbers that matched measurements. and Noether's theorem seemed too philosophical for my taste. But as I got older, as I worked on more and more problems, I started to see it differently. I realized that understanding why the laws work the way they do is just as important as knowing what the laws are, maybe more important. Because when you understand the why, you can see connections you'd otherwise miss. You can guess what new laws might look like. You can sense when something is wrong, when a proposed theory violates a symmetry it shouldn't violate. Einstein understood this. His whole approach to physics was based on symmetry. He said, "Look, the laws of physics should be the same for everyone, regardless of how fast you're moving. That's a symmetry principle." And from that one principle, he derived special relativity. All those strange effects, time dilation, length contraction, E equals mc squared, they all flow from that single symmetry requirement. General relativity is the same story. Einstein said the laws should be the same regardless of whether you're accelerating or in a gravitational field. That's another symmetry. And from that, he derived the equations that describe gravity as the curvature of space-time. The whole thing is built on symmetry. When you see physics this way, the universe stops looking like a collection of random rules and starts looking like a coherent, elegant structure. The rules aren't arbitrary. They're required by deeper principles. And those principles are about symmetry. Now, I should mention that not all symmetries are perfect. Some are broken. The universe doesn't treat left and right exactly the same, for example. There's a famous experiment showing that certain particle decays prefer one direction over the other, so there's a little bit of asymmetry there. But even the broken symmetries teach us something. They tell us about the forces that break them. And in quantum mechanics, symmetry becomes even more central. The whole classification of particles, electrons, quarks, photons, all of it is based on their symmetry properties. What kinds of transformations leave them unchanged? That determines what they are and how they interact. Symmetry is the organizing principle of particle physics. I remember talking to some students once, and one of them asked me, "Why do you think the universe has symmetries at all? Why not a chaotic mess where the laws change randomly from place to place and time to time?" And I had to admit, I don't know. That's one of those deep questions we can't answer yet. Maybe we never will. But what I do know is that the symmetries are there, and they're beautiful, and they explain so much. Here's how I think about it now. The universe is playing a game, and symmetry is the rule book. The laws of physics aren't arbitrary dictates from on high. They're consequences of the symmetries built into nature. Every conservation law, every force, every interaction, it all flows from the symmetries. If you want to understand physics at the deepest level, you have to understand symmetry. And the reason this matters, the reason I'm telling you all this, is that it changes how you see the world. Once you understand that momentum conservation comes from the sameness of space and energy conservation comes from the sameness of time, you see these conservation laws differently. They're not just rules to memorize, they're windows into the structure of reality. When you throw a ball and watch it arc through the air, you're watching time symmetry in action. When two cars collide and the total momentum is preserved, you're watching space symmetry in action. These aren't abstract mathematical concepts. They're visible everywhere, in everything that happens, all the time. I've spent my whole life trying to understand nature, and the more I learn, the more impressed I am by how it's put together. The universe didn't have to make sense. It didn't have to have simple, beautiful laws, but it does, and symmetry is why. So the next time someone tells you about conservation of energy, or conservation of momentum, or any of the other conservation laws, ask yourself, what's the symmetry? What feature of the universe is staying the same when things change? Because behind every conserved quantity, there's a symmetry hiding. And finding that symmetry is finding something true about how the world works. That's what Noether discovered. That's what I eventually learned to appreciate. And once you see it, really see it, physics is never the same again. It becomes less about memorizing formulas and more about understanding structure, less about what and more about why. And the why, let me tell you, the why is gorgeous.